Okay, so this is something how the stack will look like when I do the push command. So the push command will be done automatically when I'm just calling a function. So the 2 will be stored in the stack, and then 3 will be stored above that. And when the function we are inside the function add function, so this thing will be popped out to the add function, and this thing will be popped out to the kind of the same function as an argument. Okay, and once the function has exited, so what it will do is it will kind of clear the stack for me. So 2 and 3 will be like the stack will again look like something as something there is nothing there. Okay, so going to the code now, and as you see that I see some that there are a lot of strings, and I can't, it doesn't seem to be human readable. Okay, so there are some of the strings over here, and what is happening, I see multiple strings that are being pushed to the stack. And once it is pushed to the stack, it's the code is actually calling some function like 40212C6. So it seems like that this function sub 4012C6 seems to be like kind of a decryptor, that it is taking some encrypted value or maybe encoded value and is decoding that and kind of then returning to or saving it to some other part. Okay, so we will see like if that indeed the case, that this function is indeed a decryptor function and all. So what I will do is now quickly, okay, so what I will do is I will quickly go over here and I will add a breakpoint over here. Okay, so what this breakpoint does is when I will run this malware, and once this malware reaches this line, what will happen is like it will stop at that moment of time. It won't execute any other lines going forward. So the malware will be in some kind of a pause state, and it will stop till the time I exit from this breakpoint or go forward. So what I will do is again, maybe just for this thing, I'm again putting a breakpoint in the same function, no matter. Because this function has been called a lot of multiple of times, so I'm just going to that and just putting a breakpoint over here. And now what I will do is I will also put a breakpoint in the when this thing is gone in this string is pushed to the stack. So now what I will do is once I have set a breakpoint, because I see something interesting is over here. And now you guys both will agree that there is also a string called a service profiler, which was something, if you can recall, that when we saw the auto persistence mechanism, so there was one of this line that was getting created inside the run key. That in the run key, there was a sub key that was getting created with the name of service profiler, and it might have the exe file srvcp.exe path, so that when the system is again turned on, the malware automatically gets run. Okay, so you can see, just viewing the string, we get a lot of information over here. So the adding of so you can tell like just to add the malware to the registry. So the code is something that code is something that is executed over here. Okay, and now I am getting to this line, okay, where I will be seeing what this thing is doing. Okay, so as I have set the breakpoint, now I will go and run the malware. Okay, so I will go to the debugger menu and I will start the process. Okay, so I have started it. You just press it yes, and so you get some software exceptions. That's not a problem. So I will go.
So this is a software breakpoint, Pradyan, is it?
Yes, yeah, correct. So this is a software breakpoint, and yeah, to state that there are two kind of breakpoint: software breakpoint and hardware breakpoint. And software breakpoint is something, there might be malware sample which kind of detect this kind of breakpoint. Okay, and so it's always like kind of when you do an analysis, it's always told, okay, you guys do a hardware breakpoint, because that is something malware attacker won't be analyzing. It's very difficult from them. But for the whole course, but it's quite complicated, we need to do a lot of registry changes in our host system, and hardware breakpoint sometime also crashes the system. But it's a very good if you want to evade detection of any breakpoint that you have put in the code by the malware. Okay, so this is a very basic software breakpoint. Yes. And now it has gone to some exceptions. So I will start the process again and kind of just click on yes. And now you see that I have touched this breakpoint where I have done, where I have put a breakpoint in the push offset some string. Okay. So this is something how the interface look like. And I'll just showcase you some details now. Okay, so this is the stack that I was telling to you. Okay, so this is the RAM memory stack that has been allocated for this process. And if you see, if I go to the process hacker.
So stack is basically the memory that we are getting
Yes,
for a process.
yes. So
Okay.
you will get a lot of you will get a memory, and memory will be actually divided for a process. You will get a separate kind of memory portion, and that memory portion will have a lot of different things. Like stack memory will be there, then something called as heap memory will also be there, and a lot of other details like the memory will also contain the code of the malware itself. So those all things will be there. A lot of different things are there. It's not just the stack. And as you see, that process is running, srvcp.exe is running, and currently it is in the pause state. Okay.
Okay.
Yeah. So what I will do is now, and so this is one of the stack memory window, and this is the register window. So as I told that in the CPU, in our CPU, there are a lot of kind of a variables like EAX variable, EBX variable, ECX variable. So there are a lot of variables inside that, and a lot of data are saved inside these functions. A lot of data are saved inside this value. It's similar to kind of a variable. Like suppose when I'm writing the code, I wrote, okay, A equal to 5. That means A is a variable which stores the value 5. So similarly, you can tell EAX is some kind of a variable that is hard coded inside the CPU. Okay. And this all thing stores the lot of values. And why this was needed, because the CPU, if it has some storage capability, is actually very fast, because our value A equal to 5 will be stored in the RAM memory. Okay, but it won't be stored in the, most of the time it will, so EX will be somewhat faster. Okay, so if there are some value that is stored in the CPU, it will be very fast, like the program can access this very quickly. Okay, so CPU comes inbuilt with lot of storage. Okay, and now so EAX is something called something which is related to kind of when the function actually exit, when we return from the function, the final details normally are saved to the EAX register. Okay, now I will go to the EIP register, so you can see something as EIP. Okay, so what I tell over here is that if you see the EIP value holds 0040141D. I think it's visible, right, to both of you?
Yes.
Yeah. So the full form of this EIP value is extended instruction pointer. Okay. So instruction pointer actually tells what the line of the code that is currently executing. So if you see the value is 40141D and it matches with the breakpoint that we have set. So this is a line that is going to be executed now. Okay. So this EIP, if you see the value of the EIP, you can quickly tell, okay, what's the next instruction that is going to be executed by the process, by this EIP value. Okay. And so this is the final value. And this is something like, if you go over here, it is written 4013F0 plus 2D. So I guess like if you add both this, it will come to this value 40141D. Okay. So this is the next instruction that is going to be executed, the code that we have set a breakpoint. And now what I will do, I have to kind of go through the code one by one. So what I will do is, there are, if you see to my turtle, where the turtle is, so there are a lot of buttons over here. Okay, so this button, the first button, execute each instruction. What it will do, it actually execute instruction one by one. Okay, and so once I click that, the instruction pointer, the first line, the push command will be executed. Okay, if I execute that, and I'll be clicking this button now. Okay, so I have done that, and the first command has been executed. Okay, push offset A and H1P FW. Now, as I told, this push command is related to something storing the data inside the inside the stack memory. So as you see in the stack memory now, that this data has been actually kind of saved in the stack. Is it clear to both of you now till now?
Yes, Pragyan. Yeah.
Yeah, Pragyan.
Okay. And now if I want to tell, okay, what's the topmost data that the stack holds? So if you see that there's a pointer called as ESP. Okay. So if I go to this ESP, the value of this ESP will always point to the top of the stack. Okay. So here the ESP is pointing to the current top of the stack. That is our data that has been pushed to the stack. Okay. Now something like, suppose you want to suppose I want to save the EAX value. Just one example, I want to save the EAX value to the stack. What I will write here as push EAX. So what will happen is like the EAX value will be saved in the stack. So is it clear to both of you?
Yes.
Okay, great. So now what I will do is like, once this data has been pushed to the stack, so the next line, that is call this function, will actually kind of call this function and kind of try to do something. So what I will do is this function again will have a lot of multiple lines. So I don't want that. I just want to see the final result of this function, but I don't want to execute each instruction one by one for this function. Okay. So what I will do, I won't click this line now, that execute
F8.
instruction. Yeah, please pardon.
F8 will press F8, right?
Yeah, if I execute this, if I click this button, so what will happen is kind of I will go inside that function, and because this function might have multiple lines, maybe hundreds of lines, then I will be executing each line one by one by one. So it will waste my time. So what I want for now is just want to see what this function does to this value, to this argument. Okay. So I won't click this, but I will click the next button to that. It tells execute the instruction without entering the function. Okay. So I will click this now. Okay. So as you can see, I went to the other line. Okay. I went to the other line now and kind of inside the function. So what this function did was actually that it actually got the offset value, like the string value. And you can see that the string that was there previously, the ANH1 PWDEF, has been actually decrypted to gus.ini. So I'm stopping now for any questions as of, yeah.
Got it, Pragyan. It's decrypting the string, the second part.
Yes. Yeah. So it is decrypting those kind of, so this function is actually kind of a decryptor, and it is, yeah, any questions?
No, Pragyan.
Okay.
Yeah,
So,
Pragyan, I have a question.
yes.
So, how do we know the difference between a software, hardware, and a memory breakpoint, and where to use which breakpoint?
Okay, so thing is like, suppose you are analyzing a malware sample, and just for this sample, suppose I have put a software breakpoint, and you see that the malware is, whenever you are like running that, the malware is not kind of running properly, or kind of it is suppose it is exiting the code, it is terminating itself, or it has just transferred you to a fake loop where you are just running through the loop like hundreds of times. Okay. So that's where you can tell, okay, the malware might have detected you, that you have it has got to know that you have used a software breakpoint. That's one of the way. The other way is, before you set a breakpoint, you do the review of the code analysis, just to see like if there are some functions that the malware is importing, right? Suppose some anti-debug function, okay, where it is trying to, there are functions where kind of which can tell you which can tell the malware that, okay, by which it can check that if a breakpoint has been set, like suppose a timer. So suppose the malware knows that between the first line of code and the 10th line of code, the number of seconds that it needs to be executed is just 1 second, and suppose because of breakpoint the number of seconds is taking more than 1 minute. So using the time difference also, malware can know that there is a breakpoint. So before doing any debugging analysis, most of the time we tell that, okay, you see the anti-debug functionality if it is there in that. So once you see, okay, if it is there in that, so either suppose you set it, you see that there's a timer. So what you can do is like you set the breakpoint and you see, okay, the timer is comparing the value to suppose 2 seconds. So what you do is you go through that code and you can actually suppose the timer value is saved in a kind of a register, suppose EAX. So you can actually go to the EAX and change the timer value to again 2 seconds, even though the thing is taking 10 seconds to execute. So that's how you can actually fool the malware that, okay, the breakpoint has been set. But again, like if you see a like lot of functions where kind of it is having some anti-debug function or it's transferring you to the loop, then you decide, okay, now the software breakpoint won't work. So I'll be going forward with the hardware breakpoint, and that's how I will be doing my activity. So is that clear? Do I answer your question?
Yes, you did, but I have another
Yeah.
query. So
Yeah.
basically, when I am analyzing a malware, if I put a software breakpoint, I know what it means. Basically, before that breakpoint, every instruction will be executed. Right before the breakpoint, every execution will be executed. Every statement will be executed, and
Yeah.
then it will stop. But
Yeah.
in case of a memory and a hardware breakpoint, I don't exactly understand what's happening in the computer.
Okay, so basically in the hardware breakpoint, kind of I too have to recall, I have to check that once again. So what it does is actually you you actually does a EIP. Suppose this is the instruction pointer. So what I can do is I can use another software. So I think IDA Pro also has that functionality. So I can tell, okay, when the instruction pointer goes to is greater than this, or maybe is pointing to this line of code, so you just stop that. Okay, so I am not touching the code or not touching the code. I'm just touching my registry value, my CPU registry value, and that's how I can set a hardware breakpoint. So, but for before that, I have to actually do a review of the code analysis, like which instruction pointer I am worried about, or maybe suppose I can even tell that if the stack memory IP address, ESP IP address is somewhat this, so then you put a hold to that. So that's how you can like kind of set a hardware breakpoint. Okay.
Okay.
Okay. Yeah. So going forward, so as we can see that the strings are getting decrypted. So just for suppose for this example, I will again set a breakpoint over here. So suppose for this example, I'm repeating this function again. So I go and kind of execute the first again the line. So I see that AAHKL has been again saved to the stack, and when I execute this function, call again this function, so I will go to this, and you can see that this function has been again, this string has been again decrypted to something called as MyKey. So what this function is actually doing, it is not, and now if you see the EAX value, it is actually kind of it is not showing you the decrypted thing, but what this function is doing is like you have this push offset. So if I click over here, I can see, if I double click over here, so I can see that a string has been declared AAHKL in the data section of the executable at this particular offset. Okay, at this particular offset, and it holds a string called AAHKL. So in the same place, what it's doing, it is taking the string from this place, and then it is saving the decrypted form in the same place again. So you can see that MyKey, that this string has been decrypted and it has been stored again to the same kind of holder to the string. Okay, and so now you can see that there are other strings too, which hold some strings like WTWJR. So what it will do is like it will again decrypt the value, it will again decrypt this thing, and the decrypted content will be saved to this char array. Okay, so we will go again back to that and we will execute the code. Yeah. So now I have again, you can see that I have pushed the WTWJR to the stack memory. And now I will again call this function. So if I want to go to this function, what I can do is I won't click on execute instruction without entering the function, but I will click on this function, like execute each instruction. So if I click over here, I am now in the that function, that decryptor function now. Okay, so again I have to do one by one, and kind of you can see that it is doing a lot of activity. It is doing a XOR of like a lot of data, like suppose maybe it is a XOR encryptor, like it has a key which kind of does a XOR in decryption, and then kind of it is returning the data. So if I go over here and maybe put a just press a space over here, I can see the whole flow of the code. And as you can see, a lot of things are happening there, a lot of loops that are going there. There are a lot of loops that are going there. You can see the green line. So this is a loop. So there are some like kind of some kind of what do you say, the computation that are going on, and a loop is there. And once the loop has been completed, then it goes to the red line. So when the function has when this if else function tells okay, the now it is a no condition, then it goes to this block. And if you see over here, there's a return statement. Okay, so this return statement actually kind of does the thing. So if you again see over here, internally it is calling some function, then it is what it is doing is it is storing the value of EAX, moving the value of EAX to another register. So this all thing we will see in much more detail. Okay, so if you see, if I just highlight this, it is actually holding the kind of pointer to the AWTWGR string, and it is moving that to the EAX register over here. Okay, so this data is getting moved to the EAX register, and then it is returning from there. Okay, so if I again press the space and kind of go through that, just click over here. Just a minute. Yeah. So clicking this button, because I was inside the function, so clicking this button, what happened, the third button, what happened is like when because I was inside this function, I executed all the code and returned to the main function, the callee function actually now. So now you see that again, this function, this string has been decrypted. So now we can be pretty sure that this function is something kind of a something kind of a decryptor for us, which is doing a decryption. And now later when I do a code analysis, I can again rename this function as a decryptor. So then next time when I review the code, I won't be confused that, okay, it is something sub 401266, but it will be saved with my name, that is this function is kind of a decryptor function. Okay. And so let's complete all the analysis now and go through that and execute. So you can see I am able to decrypt a lot of strings, and there are a lot of abusive stuff too. And you can see that even over here, so it is irc.m. So it might be the host name that where it is trying to connect over here. So if I do a strings command, if I run a strings over this binary, if I just do the string, I won't be able to see the host name. But that thing was actually, thing is the whole host name has been splitted into different category, had been split into suppose 3 part, and then each of the string is kind of decrypted one by one. And what will happen is like malware will kind of truncate all the parts again, the decrypted part, and it will then try to connect to the that IP address. So what this malware is trying to do is kind of evade the basic string search, and is trying to basically hide the website that it is trying to connect to. Okay. And now the other part that as I told was that we have something called as gus.ini file. Yeah. So this was something I will just edit. So it is somewhat something decrypted. It is something which is encrypted for now. So we will also see if we can decrypt this data using the code analysis. Okay. So we have to tell, okay, where this function, where we have to see where this file is opened by this malware in a write mode or read mode. And then so suppose for this case, what is happening is the malware is trying to open this file that was existing in syswow64, and then it will try to decrypt that file. So it's some kind of a configuration for the malware, and we will see how we can tap into the code analysis they kind of like decrypt this file for us. Okay, so I will stop for now for 2 minutes, and I want to stop for any question that you guys might have.
Yeah, Pragyan. So this file gus.ini, it's embedded in srvcp.exe.
No. So what is happening? Like thing is like as I gave you the scenario that we suppose for an incident investigator we got an information that there was a suspicious process running on something port number 6667, and so this gus.ini was not actually kind of embedded in the srvcp.exe. What is happening is, suppose whenever kind of any malware attacker is trying to attack your company, it will do that in stages. So in the first stage, what it does is like maybe there was a PowerShell script that actually kind of went forward and kind of downloaded two files from the internet. That is, first is gus.ini and second is the srvcp.exe. Okay, then
Okay,
that,
okay, got
yeah,
it.
and yes, and then the PowerShell script actually put that gus.ini file inside that syswas64 folder. So now we have this file and we want to see that when we opened this file and we found, okay, this all are encrypted, and now with the code, with the help of code analysis, we will see how we can decrypt this file. Okay, so I will take a 1 minute break and then I will move forward with kind of decrypting this file. Okay.
Fine, Pragyan.
Okay, guys. So I will start now with decrypting the gus.ini file. And before I do that, what I will do is actually kind of stop this.
Pragyan,
Yeah. Yes.
yeah, last time when we opened this gus.ini,
Yes.
it was encrypted and we are unable to see. I mean, we are unable to understand whatever it is written
Yes.
in that file.
Yeah.
So now we are doing decryption for this
Yes.
file.
Yes. Yeah.
Okay.
Yeah.
So
So
using the same function.
no. We not using the same function, because thing is like that function was actually just decrypting the strings that were pushed to the stack. Okay,
Okay.
it was actually not decrypting the file. And the thing is like how you can tell that is actually that gus.ini file actually a text file that was existing prior to the malware getting started in the syswas64 folder. So
Mm-hmm.
the proper way which I will be telling you, suggesting you that this is a file, that means the malware will be actually trying to open that file for reading or writing. So that means we don't have to
Mm-hmm.
again go to the function and check where go to the same code where just to see if it is like decrypting this file. What we will do is just we will see like where is the function, open function, which is and where are the if this malware is actually calling the open function, and from which all different part of the code from which it is calling the open function, and if any of the open function is actually trying to open the gus.ini file. So this will be the normal approach for us that we will be following now to decrypt the file. Okay. Got it.
Yeah, Pragyan.
Okay, great. So what I will do is now, as I just want to give you an overview of a lot of tools in the prior classes, and then we will like do a deep dive in all these tools. So now I will not be using IDA Pro. I will be using another tool that you might use in your analysis. So that will be the Oli debug tool, and we will try to achieve the same kind of activity from the Oli debug. Okay. So just exit this. And if you see the srvcp.exe, I am sure like it won't be executing now. So I don't see srvc.exe executing. So it was executing as a child process to the IDA Pro. Okay. And now what I will do is kind of start with the code. We start with the decryption process of GUS.ini file, and I will do that with the Oli debug. Okay. So I think it will be better because the remaining time is around 6 minutes. If I do that in another instance, like if I again stop this meeting and do that, start it again, so that we don't have a break for another 30 minutes. I think that will fine, right?
Yeah, Pragyan, that's fine.
Yeah, but
Okay, sure. Yeah, I'll make sure that you guys don't have this difficulty from the next class. This is just for the first time. Okay.
sure, but